In this video, we're going to cover the structure and reactivity of benzene, looking at the key features and properties of benzene, which distinguishes it from a hypothetical molecule 135 cyclohexatriene, and the electrophilic substitution reactions of benzene. We'll look at the nitration reactions and the Friedel-Crafts reactions, looking at equations and mechanisms for both. Benzene has the molecular formula C6H6. It is a cyclic molecule, so it has a ring structure, and it is planar, which means it's flat. If you were to have a go at drawing the structure of benzene from the molecular formula, you'd probably draw something like this: a six-membered ring with three double bonds inside, giving it the molecular formula C6H6. However, this structure is incorrect. This isn't the structure of benzene. During this video, we're going to look at the evidence for why this structure doesn't exist and why the correct structure does exist. This is the actual structure of benzene. You'll commonly see it drawn as the skeletal structure shown here, but if it was to be drawn fully displayed, we would draw it like this. The ring in the centre represents delocalized electrons. So it represents a ring of 6 delocalized electrons. We're going to have a look at the structure of benzene in more detail. Each carbon atom in benzene forms a single covalent bond to the two carbon atoms it is joined to, and a single covalent bond to one hydrogen. This leaves each carbon atom with a single unpaired electron in its p orbital that sticks out above and below the plane. As each carbon has a delocalized electron, this forms a ring of delocalized electrons, which was represented by the circle we drew on the previous diagram. That's why this topic is called aromatic chemistry. Organic molecules with delocalized systems are called aromatic molecules. Molecules which aren't aromatic, so pretty much all the other organic molecules you've looked at so far in A-level chemistry, are called aliphatic molecules. Having a delocalized ring of electrons makes benzene very stable, which means it is very unreactive. If a molecule is stable, it's not energetically favourable for it to undergo a reaction. Benzene does undergo some reactions, and we're going to look at what those reactions are and why they happen later in the video. We're now going to look at the evidence why the structure on the left is the correct structure of benzene, and the structure on the right is incorrect. A scientist named AQA came up with a structure on the right which isn't correct, so you'll sometimes hear this referred to as the AQA model or the AQA structure of benzene. So if we take a sample of C6H6 or benzene and we measure the bond lengths in it, all of the bonds in benzene are the same length. So all the carbon-carbon bonds are the same length. This means the AQA structure, or cyclohexa 135 triene, can't be the correct structure of benzene. In the incorrect AQA model, it should have 3 long bonds for the single bonds and 3 shorter bonds for the double bonds. Just remember in the work you did in the very first topic, Introduction to Organic Chemistry, where double bonds are shorter than single bonds. So since all the bonds in benzene are the same length, that provides evidence for the delocalized structure of benzene, because all the bonds in benzene here are the same length. In our hypothetical model, cyclohexa 135 triene, we should have 3 long bonds and 3 shorter bonds instead. From the work you did in the alkenes topic, you should be aware that alkenes will react in electrophilic addition reactions with an electrophile. So for example, an alkene reacting with bromine water to decolorize the bromine water and form a dibromine alkane. Now you'd expect the AQA model of benzene to react just like any other alkene. Cyclohexa 135 triene has got 3 alkene double bonds in, therefore it should react with bromine or a similar electrophile. However, benzene does not react with electrophiles like you'd expect it to do if it was an alkene. So, since benzene doesn't react through electrophilic addition, it can't have the incorrect structure, it must have a different structure instead. As we've already discussed, having a delocalized ring of electrons makes you more stable, therefore unreactive, and that provides further evidence why benzene's structure is the model on the bottom rather than the top, as it does not react with electrophiles like you'd expect it to do if it was an alkene. The final bit of evidence for why the benzene structure has a delocalized ring as opposed to the kekulé structure with the 3 double bonds can be found by looking at bond enthalpies. In particular, we're going to look at the hydrogenation bond enthalpies. So the enthalpy change when we hydrogenate or we react a double bond with hydrogen, turning the alkene into an alkane. Now, the kekulé model is hypothetical because it doesn't exist, but we can work out what its bond enthalpy of hydrogenation should be. We know what the enthalpy of hydrogenation is for cyclohexene. So I've drawn cyclohexene here, and if we react cyclohexene with hydrogen to remove it to form cyclohexane, the enthalpy change is minus 120 kilojoules per mole. Therefore, cyclohexa-1,3,5-triene, or the kekulé structure, should have an enthalpy of hydrogenation of minus 360 kilojoules per mole. And that's because if one double bond in a 6-membered ring to hydrogenate has an enthalpy of minus 120, if we've got 3 of those double bonds, we'd simply times that value by 3 to get minus 360 kilojoules per mole. However, when you hydrogenate benzene, the enthalpy change is minus 208 kilojoules per mole, which isn't the same as the minus 360 we would expect if this was the actual structure of benzene. Therefore, we can say that benzene is 152 kilojoules per mole, more stable than the cyclohexa-1,3,5-triene hypothetical structure, which further supports the evidence for the delocalized ring, because not only are the enthalpies different, benzene is actually more stable, which fits with the properties of having a delocalized ring of electrons. Benzene reacts through electrophilic substitution mechanisms. The benzene ring is an area of high electron density, which attracts electrophiles, electron pair acceptors. Benzene will undergo electrophilic substitution reactions. It won't undergo electrophilic addition reactions like other alkenes do, as this would break the delocalized ring if we added on 2 new groups to 2 of the carbons. This would therefore reduce the stability of benzene, so given it would break the ring and reduce the stability, those reactions don't happen. If we do a substitution reaction on benzene, replacing one of the hydrogens, obviously not shown in this case because it's drawn skeletally, with an electrophile, the benzene ring will remain intact and the stability of benzene will remain the same. So in electrophilic substitution reactions with benzene, we substitute one of the hydrogen atoms from the benzene with an electrophile. The first step of the mechanism is the electrophile being attacked by a pair of electrons from the benzene ring and forming a bond with one of the carbons. We show this by starting our arrow touching the benzene ring and then drawing the arrow to the electrophile. This partially breaks the delocalized electron ring and gives the molecule a positive charge. You have to be really careful when drawing this intermediate structure. Even though we've drawn the rest of the benzene skeletally, you need to show the hydrogen at this point, making sure we've shown it on the same carbon that we've added the electrophile to. When we draw the delocalized ring, when it has been broken in this intermediate structure, we need to make sure the ring starts and stops on the carbons 1 bond away from where we've added our electrophile to. So if we notice, we've added the electrophile to this carbon here, so the ring will start 1 carbon away and finish 1 carbon away, We then draw a positive charge in the middle of the benzene ring. To regain stability of the benzene ring, the carbon which is now bonded to the electrophile loses a hydrogen, as shown by the arrow we've just drawn. This will give us our final product, showing how we've substituted one of the hydrogens for the electrophile. We're now going to look at two specific examples of electrophilic substitution. The nitration of benzene involves adding a NO2 group, a nitro group, to benzene. To do this, we react benzene with nitric acid and a sulfuric acid catalyst to form nitrobenzene and water. The sulfuric acid catalyst reacts with the nitric acid to form the nitronium ion, the NO2 plus ion. This is the electrophile in the reaction. Nitric acid is not a strong enough electrophile by itself to react with the benzene ring. So we must make the nitronium ion as part of the reaction. If we didn't have the sulfuric acid catalyst, this reaction wouldn't work, as we need to turn the nitric acid into a nitronium ion. You need to learn and to be able to reproduce this equation in the exam. You'll need to give this equation whenever you draw the mechanism for this process. Now we've generated the nitronium ion, we can draw the mechanism just like we practiced a moment ago. The first step is the benzene ring attacking the electrophile, forming the intermediate structure with the hydrogen and the nitro group shown on the same carbon, and our broken delocalized ring, starting and finishing one carbon away from where we've added our new group. And finally, losing the hydrogen to reform the delocalized ring, giving us nitrobenzene, where we've substituted one of the hydrogens for a nitro group. If the temperature of the reaction is below 55 degrees, we'll just add a single nitro group to benzene. It'll be monosubstituted. Above this temperature, multiple nitro groups can be added. Nitro compounds decompose violently when heated, so they're used as explosives. I've modified this molecule so it is now 2,4,6-trinitromethylbenzene, previously called trinitrotoluene, or TNT. So nitro compounds are used as explosives. An acylation reaction of benzene, sometimes called a Friedel-Crafts reaction from the scientists who discovered it, is where we add an acyl chloride to benzene to form a phenyl ketone and hydrochloric acid. An acyl chloride, as we've looked at in topic 9, is very similar to a carboxylic acid, apart from it has a chlorine in place of the OH group. If we react the acyl chloride, again the R group here can be any length of carbons, with benzene, using an aluminium chloride catalyst under reflux, we will form a phenyl ketone, so adding a ketone group to benzene, again R being however long the carbon chain was on the acyl chloride, and hydrochloric acid. As with the nitration reaction we looked at a moment ago, the acyl chloride isn't a strong enough electrophile by itself to react with benzene. That's why we need to react it with the aluminium chloride catalyst. By reacting the acyl chloride with the aluminium chloride, we will remove the chlorine from the acyl chloride and form the positive ion which we can then use to react with the benzene. So we've now got the benzene and the electrophile we generated in the previous step, remembering you need to be able to write the equation to show how we generate this electrophile. The first step of the mechanism is the benzene ring attacking the electrophile. We then draw our intermediate structure correctly, and then show the hydrogen being lost from the intermediate structure. giving us our final product of a phenyl ketone.